E como temos alguns participantes cuja língua nata não é o português, tem uma dificuldade com o português, então o professor Valério vai apresentar em inglês. Então eu vou agora fazer a apresentação dele em inglês e a apresentação vai ser em inglês. Na hora das perguntas, aí pode ser em português ou em inglês, a gente vai combinando as duas coisas. Ok?
Okay.
So, good afternoon, everybody. So we are continuing our seminars. Today we have Professor Valerio Carruba, and so he's going to give the talk, and then we may have questions at the end of the presentation. So thanks for the presence of everybody. So please, Professor Valerio.
Thank you very much. Thank you all for being here during these difficult times. So today I'm going to talk about two passions of mine, which are astrodynamics and more recently machine learning. So I hope you can all see the screen. If you have some problem, please feel free to interrupt me. So this talk is about a new method for classification of asteroid family members, or more exactly, a way to find new members of asteroid families, knowing what the old members are. So what are asteroid families for people that are not working in the field? Asteroid families form as a result of collision or rotational failure of a parent body. And they are identified by similarity of proper element like semi-major axis, eccentricity, or sign of inclination, or proper frequencies like the mean motion, the precession frequencies of pericenter or nodes. Proper elements are constant of the motion and are stable over time scales of million years, contrary to the case of the oscillating orbital element. So in the figure you can see some of the most important asteroid families, Eunomia, Massalia, Themis, etc., and they appear like clusters of objects in the space of proper semi-major axis versus sign of inclination. Okay, for many years, the most commonly used method to identify asteroid family has been the hierarchical clustering method, or AdaBoost. So how does this work? First, we check if there are objects that are closer to a parent body than a distance cut off, or for instance, in proper element domain. So you check if two objects are closer than a distance limit. If you find a new object, this is a new member of the asteroid family, and then you repeat the process for this object as a parent body until you find no new possible family members. So usually you construct what is called dendrograms. And here, for instance, if you see the red lines, this will be the equivalent of an asteroid family. This is an example for customers and in Euclidean distances, but the concept is the same. Essentially, these red lines will all be associated with a single cluster. So what is the problem with AdaBoost? AdaBoost is applied to asteroid families is a method that was introduced in the 90s when the number of asteroids which was known having a reliable proper element was of the order of 10,000, 20,000 by the mid-90s. Nowadays, because of robotic surveys and automatic discoveries of asteroids, the number of asteroids for which we have proper parameters of the order of 750,000 asteroids. So several order of magnitude higher than what is when the method was introduced. And this is a problem because if you have two asteroid families that are nearby, they may merge when you consider also the halo. So the AdaBoost may have problems in distinguishing between families that are nearby. There are methods to resolve these issues. For instance, some were introduced by Andrea Milani in one of his last papers, but these are not simple and they are computationally demanding. So here is where you can introduce machine learning. Supervised learning have been developed in the Python language in the last year. So what is supervised learning? Imagine that you have a problem where you have bananas and apples, like in the figures. You can train a model to recognize what is a banana and what is an apple, said in very simple terms. This is an example of supervised learning. So based on non-existing population of objects, you can classify new object based on the properties of the object that you already know. So there are several free available packages for use of machine learning, for instance, scikit-learn package by Pedregosa in 2011. And now, since 2017, there have been several papers on the application of machine learning to astronomy, in cosmology, the study of supernovas, the study of solar flares, etc. The number of applications to astrodynamics is still somewhat limited. There is a paper in 2017 by Smirnov and Markov on asteroids in three-body resonances. And then there is our paper on identification of families in low number density regions of the main belt by hierarchical clustering method. But this is pretty much it. That I'm not aware of other papers on the subject. So you can have two kinds of supervised learning algorithm. You can have what is called standalone or single algorithm and ensemble method. Ensemble method uses several standalone algorithms to obtain a result. So you can distinguish between the bootstrap aggregating, also called bagging, where the training data is split into multiple samples called the bootstrap samples. Each model is accounted with the same weight. So you divide the training method in several samples. You train the models on these different samples, and then you take average, or for problem of classification, a vote of the result of each single model. In boosting, you emphasize the training case that the previous model misclassified, and the standalone models which perform better. So here you have what is called a weighted average. You tend to give more weight to models that perform better, or to data that was not fitted best by previous iterations. So this is a very simple way to distinguish between bootstrap aggregating and boosting. So what is the goal of this work? The goal of this work is to try to classify new asteroid members as members of families. So if you know that you have a population, for instance, of a few thousand asteroids, and you have a new set of asteroids with proper element that has been published, how many of the new asteroids could be classified as members of these families? So we try several standalone and ensemble methods. And the first method that we tried is called linear regression. Linear regression searches for a linear relationship between an independent variable, which is a dependent one, or y or output. So we use the proper element data from the family to train, and then compute a probability for asteroids in the standard database that they may belong to a family. The asteroid is assumed to be a family member if the computed probability is higher than a threshold value, which is a free parameter. So here, for instance, you have the probability distribution for all asteroids in a new standard dataset to belong to a family which is called Watsonia. And the vertical dashed line is the 85% level. So here, in this case, an asteroid is assumed to be a member of the Watsonia family if the outcome of the linear regression algorithm is with a probability higher than 85%. Other method which is used as a standalone method is the key nearest neighbors, or KNN. The basic idea is to predict the state of a point based on its close neighbors. So, for instance, imagine that you have the star in the figure, and you want to know if the star belongs to class A or class B. You can check for instance, for the three closest neighbors to the star. In this case, you have three neighbors and two of them belongs to class B. So the majority of vote is for class B. So the star will belong to class B. If you had a larger sample, for instance, 5, and then you would have classified the stars as a class A because the majority of members in these neighbors will be class A blue points. So this is a three parameter of the average, which is the number of neighbors used for classifications. And this is something that you need to estimate all the time that you are using this machine learning algorithm. So the last one of the standalone methods that I'm going to discuss is the decision tree. So imagine that you want to decide if you want to use a kite site. So you need the weather to be windy, sunny, and with low humidity. Otherwise, you will not be able to fly the kite very well. So you have to take several decisions in form of a tree. First, you need to know if the weather is windy or not. If it's windy, you have to know if the weather is sunny or is rainy. If it is sunny, then you need to check for humidity. So every time that you go to this binary decision, essentially you are bifurcating, taking decision in form of a tree. How many nodes you can have? This is called the maximum depth, and this is a free parameter of decision tree algorithms. So you can train a decision tree algorithm to decide for you if you want to use a kite or not. So I won't have the time to go to all the ensemble method, but I'm going to give you an example of bagging classifiers and boosting classifiers. So for instance, the extremely randomized tree. This is a bagging method. So you use several predictions from different decision trees that are trained on different set of the data. So the difference, for instance, with bagging classifiers for the extremely randomized tree is that you use sample data without replacement. In bagging classifier, you replace casually a fraction of the data, so you can have overlapping of data, repetition of data, sorry. But in extremely randomized tree, this is not the case. So you're using data without replacement. So what do? You train the first model, the second model, the third model, and for each of the model, you see the outcome of the result. And then you take a majority vote. So the model that, the result, the outcome that has the most of the vote by the models is the one that is voted out by the random forest or the extremely randomized tree method. And this is the final outcome of the method. What is the advantage of this? That you're using several different models, so you can actually combine several weak learners into one more precise algorithm. And this is the advantage of ensemble method, usually with respect to standalone approach. Okay, boosting. There are several boosting algorithms. Again, I don't have the time to go through all of them, but I just would like to give you an idea. So boosting algorithm tracks the model that provide the less accurate prediction, assign to them lower weights. So if your model was not very good in the previous iteration, it will be counted with a lesser weight in the next iteration. So you will give a higher weight for model that performed best. So instead of having a democracy here, you have a weighted average of the outcome. So the model that performs best, the samples that are underclassified, these are the ones that are given more weight as the outcome of the final result. So you have several kind of adaptive boosting models. One of them is adaptive boosting, but you also have the gradient boosting and the stream gradient boosting, which is one of the most highly performing method among boosting algorithms. So how does it work for asteroid family, which is the main topic of this talk? We selected 21 asteroid family in the inner, central, and outer main belt on low inclination, so inclination less than 20 degrees. I use family from the asteroid family portal, which is web applications that allow you to download the information about asteroid family, proper element, and similar data. So we divide the sample into two parts. One with low absolute magnitude, which is the training sample. And the rest, the test sample is the one that will be fit upon. So you train the sample, you train your algorithm on the training sample, and you predict the data of the test sample. Why we use this 14 absolute magnitude equal 14? Because objects with a low absolute magnitude are less likely to be affected by chaining. So you are more sure that the families that are determined in this sample are really separated and not joined together. So how does it work? We train the learning method to the proper distribution in proper element of the asteroid or the training sample. So you have an asteroid family, you select the objects with magnitude less than 14, you train the method on the distribution in proper A scenarii of the sample. And then we use the method to predict what are the members of the family at higher absolute magnitude. And then we can compare the result, the outcome with the actual data from standard ASM. So we can distinguish between what we call true positives, that are predicted to be family member by both methods, machine learning and ASM. False positive are asteroids that are identified as family members by machine learning algorithm alone. And false negative are asteroids not identified by family member only by the machine learning algorithm. So these asteroids that are missed by the machine learning algorithm. So we need to quantify the goodness of our fit. So we can introduce some parameters. In particular, we define completeness as the number of true positive divided by the number of true positives by false negative. And this may give you an idea how much you are able to retrieve the original population of asteroids or family members. If you have a good completeness, it means that you have found most of the objects that were in the original asteroid family found by FSM. This might not be enough, because imagine that you have a family of 100 objects and the machine learning algorithms find a family of 10,000 objects with include all the 100 objects in the original population. You will have a completeness of 100%, but this obviously is not a good fit of the family. So we also define a precision factor, which is the number of true positive asteroids divided by the number of true positive divided by the false positive. So this measure how precise is the retrieved family. If you have a large number of false positives, so for example, that we discussed before, if you have a family of 10,000 objects, which has essentially most of the objects as false positive, the value of precision will be very low. So you may have completeness factors that are high, a precision value that are low, or vice versa. You can have high precision but completeness that are very small. So you needed to make a trade-off between the two factors. And this was done in our work by combining the two coefficients into what we call final parameter. This is given by a weighted average of the two parameters, 1/2 of the completeness square by precision square. So just to discuss some more technical stuff, and then we go to a more interesting part of the talk. As we discussed when introducing the machine learning algorithm depends on three parameters. The KNN depends on the number of closest neighbors. The decision tree depends on the number of branches on which you want to divide the trees, and so on and so forth. So we needed to determine what is the best values of these three parameters or hyperparameter. So this is called hyperparameter optimizations. And how is it is done? You can try several values of these three parameters. For instance, using the grid search CV approach of the scikit-learn package. And then see what of these three parameters give you the best fit for each given family. The best value of the parameter, the mean values of the FP coefficient, can then be computed for each model. So the figures show you the distribution of the probability cutoff for the linear regression, which was the hyperparameter for this model, and the final parameter for linear regression, which was of the order for most of the family studied of 0.7 or 70%. So you have studied 9 different machine learning algorithms applied to these 21 asteroid families. And for each study family, we verified which algorithm provided the best performance measured by the final parameter. So for 10 out of 21 of the studied families, the ExtraTree method had the best performance, which has the highest values of final parameter. The second best performing was KNN, and the third one was SGBoost. So ExtraTree performed with family with a large population of objects of higher magnitude, so smaller objects. It comes back second best in many other cases. KNN performs well for small or medium families that are less than 150 members. So what do you see in the figures? Is the distribution of the members of the family that were used for training the algorithm. The black points, the red dots are the members of the family found by the machine learning algorithm that best performed in both cases. So for the Coronis families, we have the ExtraTree algorithm. For the Ventas family, we have the KNN algorithm. So we tested this algorithm also for other families that were not included in the first phase of the study, and we confirmed that ExtraTree was the algorithm that outperformed the other machine learning algorithm in most cases. So this tends to be the preferred algorithm for studying membership of asteroid families. So, but this is not the main use of this tool. The main goal of this study was essentially to have an algorithm that was able to automatically retrieve new member of asteroid families given known populations. So once we selected the ExtraTree method as one of the best performing tools, we tested how this works for real life problems of identifying new asteroid family members. So we take a real asteroid family as given by the asteroid family portal and use the ExtraTree method to predict what are the new members of these families among objects that have not included in the sample for which the AdaBoost was used. So we trained on the asteroid families, and then we trained on the untested new asteroids dataset. So we used the ExtraTree approach to choose 4 asteroid families. The Ecker family, which is a small family of about 155 members, the Ansa family, 1,484 members, Eunomia, more than 6,000, and Karin, 480 members. Karin was included because it's a subfamily of the much larger Coronis family. We wanted to see if the algorithm was able to distinguish between asteroids in high-density regions. So again, you have the black dots as the original families, and the red dots as the new-found possible members of the families. So these are the red dots are the possible members that are found by the machine learning algorithm among asteroids that were never tested with AdaBoost. So these are really new results. And you can see that they follow quite closely the orbital distribution of the original members of the families. And we actually have a way to quantify this, and for most of these, the family that we studied, results are very good. Essentially, we were able to get precisions of the order of 97% concerning the distribution of orbital talent. So, I think we can go to the conclusion. We selected 21 asteroid families that have a statistically significant population of large objects, and then applied 9 different machine learning algorithms. They used 3 parameters to characterize the efficiency with which the algorithm identified new family members were compared to results of traditional AdaBoost. We used standalone bagging classifiers, boosting method for this purpose. And among the studied algorithms, the Extremely Randomized Tree has the best performance, followed by the KNN method and by the stream gradient boosting method. So you have one bagging method, one standalone, and one gradient method. But by far, Extremely Randomized Tree was the best that we found among the studied method. So we adapted the code for the purpose of automatically updating family membership, and we tested them with the cases of small, medium-sized, and large asteroid families. So in all tested cases, the orbital distribution of the newly found member is highly consistent with the distribution of previously known objects. And the Python code that we use for this task is publicly available at the GitHub Asteroid repository. So this was really first exploratory task in this world of machine learning, which for a group is very much new, and that was something that we have been doing only from 1 year. I really welcome any inputs from the scientific community on how to improve these algorithms. So if you have a suggestion, comments, if you find that there is an algorithm that outperforms ours, please feel free to contact us. And as I told you, the codes are available at the GitHub repository, which is the second link in these final slides. And I'm also happy to inform you that the article that we submitted to Monthly Notice on this topic has been accepted for publication today. So this is really a very, very new result. Thank you very much for your attention. And I think we can go to questions if you have any.
Okay, Valerio, thanks for the presentation. So Valerio is open for receiving questions or comments. So anybody?
Hi, this is Damia. Can you hear me well?
Sure. Hi, Damia. How are you?
There you. Thanks for the invite and thanks for the really good presentation. It was very interesting and very good science. I mean, obviously we have come very long way since the classical HCM method with what you are presenting now. I just have a question about so you said the best of all methods, the best of all the algorithms is the extremely randomized tree. How good is it compared to the others? Is it by factor 2, 3, or can you quantify that?
Is not by factor 2 or 3, it's something more subtle. The second best is a K9, which is a standalone method. And sometimes the difference in the final parameter for each family that we studied is of the order 0.02, 0.03. So when we say that one of the methods is the best, it's because it's sometimes has a very small difference. It finds more asteroids, just a few more asteroids than the other method. Overall, several of the methods that we study are very good. Some of them are not. Linear regressions is very bad for this purpose. So it should not be used in our opinion. But among the others, extremely randomized tree is very good. K9 is very good for families that are small or medium sizes. So sometimes K9, despite being just a standalone method, actually perform better than ensemble method, but for a small family. Then you have this gradient method like AdaBoost, XGBoost, which is a very powerful gradient method that has been very popular in the last 3 years. And these are also relatively well-performing algorithms. It's just that our goal was essentially to try to find one single method that can work for this problem. Imagine that you have to work on this in a couple of years. You will not have the time to remember all the fine details of which method is better.
And can this, please, algorithm also able to identify subfamilies or even new families?
Not new families. These algorithms, there are algorithms that are able to identify new families. There is the hierarchical clustering method that not the classical one, the machine learning one. And this was something that actually we published last year. But this is expected by chaining as well. So you can use this method for only for low number density regions in the main belt. It's something like the highly inclined asteroids in the inner, central, and outer main belt. And actually, we find 2 new families with this method last year. But then, if you go to high density regions, you still have the problem of chaining. So you may find a large family, which is the conglomeration of 2 or more families, if you use this method blindly. So it's a difficult problem. What is the advantage of using the method that we find in this work? Imagine that you want to work with an asteroid family, and you only have the data that are in the publicly available database. sometimes this data is outdated by several months. So after the publication of this data, there have been hundreds of thousands of asteroids, new asteroids have been discovered. You don't know how many of them can be potential family members. Doing a study by AGSM by yourself is very time consuming. And so you need also to account for several factors that are not going to discuss. These codes are very fast. Essentially, if you want to know which new asteroids can be potential new member, you run these codes in less than 2 minutes. You have a very reasonable estimate of what can happen, so what new asteroids can be a member of this family, at least in our opinion.
Thanks.
Hey Valerio, Joe Massaro here. Thank you for the invite. It was a really interesting talk, and I'm glad I was able to join you remotely, since we're all remote. I did have a question on how well these algorithms work with incomplete data. Could you start putting in color parameter, albedo parameter, sizes as a way? Can it handle if some asteroids have that label and some don't?
There are methods to work with incomplete data. We didn't do that in this work. As I told you, this is just really an exploratory work. We really wanted to have a map of how the algorithm works for different problems, and to see what was possible. But yes, it's absolutely possible to work with incomplete data. There are methods in Python to deal with incomplete databases. So this could be really something that can be tried. Is really takes some more expertise than what we have at the moment, but actually that is very doable.
Okay, excellent. Thank you.
Hi, Valerio. It's Judy here.
Hi, how are you?
Hi, Valerio. Well, one of my question was I think basically answered from your answer to Daniel. That is, how would what to do with new class with new families, since I think your method will not identify them. But the point is, if you have a very large sample of objects, and you know, in the middle of this many objects, there are many which belong to a new or not identified family. What would the method do? They would just put them apart as outliers, or they would try to the method would try to classify them in one of the existing families.
Well, so the question is, imagine that you have a lot. If I understand very well your question, because the audio here was not very good, but imagine that you have you work with the data for Asteroid Families Portal, for instance, and you have a family that were determined with a sample of 500,000 asteroids, more or less, give or take. Nowadays, there are 700,000 objects, so you have 200,000 more that you don't know what the status is. So some of them can be members of new asteroid families. So there are methods to study these new asteroid families once you remove the unknown members of old asteroid families. Some others may be newly discovered members of old asteroid families. So this method will allow you to identify the members that are the objects that are more likely to be members of non-asteroid families. If you know what is the distribution of element of old asteroid families, so the algorithm will be able to go in the new data and pick up the new possible members. Once you eliminate these objects, then you can apply other method, standard AGSM or machine learning AGSM, to identify new asteroid families. Is this answer enough? I'm not sure I understood your question completely.
Yes,
so.
yes. It's okay. I understood.
Okay.
Thanks a lot.
Sure.
An excellent presentation. Thanks.
Thank you very much.
Hi, this is Emily. Thank you for the invitation and the presentation. I am not an asteroid person, so this might be a very simple question. But when you are working with this data, what is the input your input data are like trajectory parameters that you are using to classify these things?
Well, we use proper elements of asteroids. So these are constant of the motions. If you use the osculating elements, these are the instant orbital elements of the asteroids. These orbital elements change day by day, hour by the minute, essentially, because of perturbation by other planets. So you can obtain what is called proper elements, which are the elements that you obtain after you remove the perturbation from the planets. There are two ways to do that. You can do it analytically, but this is no longer done because the models are complex and the outcome is not very accurate anymore. Or you can do it numerically. There are techniques that are based on Fourier transform of data or time series to get synthetic proper element, they are called. In this domain, if you remember the second figure, then asteroid family will appear as blobs, essentially. You have a distribution of objects, which is the background, and then you have these blobs, which are the asteroid families. This is what we are using. Does that answer the question?
Yes, great. And then I have just another question about the training sample. So you said that you made a cut in magnitude, if I understood correctly, in order to choose the objects that were more certain. Is that correct? When you do this cut in magnitude, right? So my question is that cut a hard cut? Like, my question is there any object in your target sample that has age lower than 14, or all of them are put in your training sample?
Imagine that you have a family. You will have the majority of the population with these small objects. Absolute magnitude is inversely proportional to the diameter. So if you have a small object, you will have a magnitude very high, 15, 16 or more. If you have large objects, you have a magnitude that is low. It also depends on the geometric albedo, how much fraction of the light is reflected, but more or less this is it. In the initial phase of the study, we have to understand what is the algorithm we are going to use later on. So we have to train the data and have a sample of object where you can actually see how good is the outcome of the algorithm. So what we did was we take a family, we divide it into parts, and we take the object with less than 14 in absolute magnitude, because these objects are less likely to be spread out. So you don't have this chaining problem that I discussed at the beginning of the presentation. We train the algorithm on this part, and then we check how many of the objects that are have magnitude larger than 14 are found as to be member of the family by the machine learning algorithm. And then we can compare, because we know what are the objects that are larger absolute magnitude that are actual member of the family as found by standard ICM. So this is something that we can actually do to have a quantitative estimate of how good the model are. The last part of the talk, when I show you the results of the algorithm on extended sample proper element, and then we don't know what the real family is, because nobody has studied with AdaBoost these larger samples. So in this case, we really have to trust the algorithm. But in order to do that, we need to do a long preparatory study, and this is what we did in 2/3 of the paper. Does that answer the question?
Yes. Okay, thank you.
Sure.
Okay, any further question or comments? Okay, I think we can thank Valerio for the excellent presentation. And
thank you.
I'd like to thank all the participants. So thank you very much. For the Brazilians, we continue after the seminar with some local discussion. Thank you very much for everybody.